Baker Botts, LLP, provides podcasts for educational purposes only. They are not legal advice and are not intended to establish an attorney client relationship. This communication may constitute attorney advertising.
Welcome to AI Council Code. The AI Council Code is here to keep you up to date on all AI legal issues arising in the modern business frontier. I'm your host, Maggie Welsh, and today we're back with Baker Botts intellectual property partner Mark Spiegel and Dr. Pablo Rivas, assistant professor of computer science at Baylor University and an expert on large language models. In our previous episode, Mark and Dr. Rivas discussed what is AI and how do we define generative AI. Today we're back to continue their conversation where they'll be discussing the status of AI, where AI is going, and what challenges it currently faces. So let's rejoin Mark now.
How do you make a model? We talk about these models doing all these cool things, then you just say, we don't really know how they do it. And I think that's a really fascinating question that smart people like yourself are making these models. And even though you create it, you don't know what it's doing. So maybe just describe the process that you'd go through if you were trying to create a language model right now.
Sure. Well, one of the big problems of not knowing what it's doing is primarily because, for example, one of the most successful large language models is OpenAI, ChatGPT, or GPT 4.0, or one of those versions. But they have not released it. So we have no idea what exactly is the model that they have. Even they haven't released that, which we can talk about intellectual property later, but other models prior to ChatGPT were released in the public, and we knew what was going on, and we were able to tell exactly what was happening. And one thing that I need to differentiate is knowing what is happening and explaining why a decision was made. There are different things. Let's say that I have a car and I know about engines, and I can tell you what happens when you push the gas pedal all the way to having the car move. And so I know that it's gas being put in a mix with air and the carburetor, and then it's an explosion that triggers the motor to run. And so I know exactly what pieces move. I know what's happening, but I may not be able to explain that if I am giving a new car that I know nothing about, and the car, I know that it must have an engine.
The Tesla moves when you push the pedal, but there's not an engine doing the same thing.
Right. So it's different. And until I'm given access to it, I might not be able to explain how or why the car is moving. I know it must be doing some processing of energy throughout so that we can get motion. But until that is released, we don't know exactly what's going on.
So we know that ChatGPT or the 4.0 of the GPT, you can push the pedal and make it go really fast, but we don't know exactly if that's an internal combustion engine or what's going on under the hood that's making it do those things.
Right. And we know hints because of things that have been leaked, but really is input text that is being translated into tokens or subwords. Those get translated into vectors. Those vectors are processed by other vectors inside the AI engine, if you will. And that's the part that we don't know exactly what is happening. And then we get output that is produced at the end.
So where does that vector engine come from? I assume there's not somebody actually coding lines of the ChatGPT model, right? How do you get that model? Is it created by a neural network? Is it created through some other process? Or what does that look like to actually generate those models?
The word we use is trained, and the training process is a very nice algorithm that was designed about 15, 20 years ago that exploded. It's called backpropagation, gradient descent. And the idea is it's a teacher-student model.
And do all large language models use the same algorithm they're talking about for training?
In a big picture sense, yes.
Okay.
But there are subtle differences on how that is done in practice to speed up the process or to achieve specific goals. But in a general sense, a teacher student, so we give training data, and that's the teacher that tells us, here's some data. What do you do with it, student? And if student says, oh, I'm going to do this, if the outcome is correct, then great. If it's a mistake, then the teacher would say, slap in hand, try again. And the degree to which the slap hurts is the force of the update that the student needs to make. The big slap, you need to make big changes. Small slap, it's the small change. And that is what we call the degree of the gradient or the length of the gradient.
Okay, so you have an algorithm that's going to take your training data and it's going to give test questions of some sort to the model student. And based on what the model student's reaction is to the training test information, the teaching algorithm will tell it to correct one way or the other in terms of what that vector is doing with the individual input. Is that right?
Exactly.
Okay.
And so now the newer capability is focused on making that process faster and making it achieve different goals. That maybe it's not just one teacher, maybe there's multiple teachers, and every teacher has a different objective to meet. Not only that you're correct, maybe, but also that you are short in your answer, or maybe that your answer has certain properties. And when you put those together, then you have a number of teachers that are guiding the learning process. And that's when it gets different depending on what application, if you're using language or computer vision.
So for modern model, like we think about ChatGPT or Sora or any of the other AI models that are out there right now, how many teacher student algorithms would we be talking about? Is it 100? Is it 1,000,000? What's the scale here we're talking about?
Well, the algorithm itself of backpropagation in general is just one, but the variants of it, I mean, there's too many out there to give you an exact count, but I could make you one right now that is unique and different from everything else. But if we're talking about the successful ones, I would name unsupervised learning, supervised, reinforcement learning. We have self-supervised learning, and those are the top types of learning that involve some type of supervision or teacher. Personally, I like the self-supervision in which you give the AI model a time to learn on its own with minimal supervision. And then once you have that warmed up, I call it, then I'll teach it exactly what I need it to do.
Why do you like the self-supervised model?
I think it causes less bias. For example, let's say that I'm creating a model or an app that is going to recognize cats. I could go and download or get a lot of pictures of cats and other things that are not cats. And if I train the model supervisedly, single teacher that is teaching this is a cat, this is not a cat, presenting images of both, then that model would probably learn things or features of the input data images that are not necessarily related to a cat. The problem with that is that if you think about it, most images of cats might be on a couch. So how do I know that the model is not learning that whenever there's a couch, it's a cat? And what I want is not to have that type of bias. So what self-supervision does is usually that if you have all these pictures, I'm just telling it, here are pictures of things, learn about things. And once it got really good at learning about things, whether cats, couches, grass, whatever, then I can take that model that is trained on a generic perspective of the world, and I tell it, okay, focus on cats now. And that's when it gets much better and less biased towards specific things.
This is a great example. I want to continue our cat AI app here. So what does it mean for it to learn on its own about things generally? Is it learning how to differentiate the different features in the photos and to say, hey, these are all the photos that have green backgrounds. These are all the photos that have blue backgrounds. It's just feature-wise identifying similarities, or what is the learning going on under the hood there?
One of the most popular things in this space is called an autoencoder. And the idea is that I give it a picture of something. Let's say this time I'm giving a picture of a cat. It's going to try to learn a vector representation of a cat. And then using that through machine learning, let's call it a neural network. And then there's another piece to it that is going to use as input this vector representation. And its only job is to reconstruct the image of that cat exactly as it was presented in the input. So we're asking this to go into a sort of bottleneck compression stage of compression of knowledge. And here's a picture, give me a vector, and I'm going to use this vector to reconstruct the cat perfectly. And so if I do that for a lot of objects, it's going to learn to represent anything in a very small vector, and it's going to reconstruct that.
So what it's learning in the self-supervision process there is how to make vectors that are uniquely associated with all of your training data.
Right. And so it will learn what is important about this image that I can represent in a vector. And then language functions in a similar way. You can also find a paragraph or give it sentences, and it will learn to reproduce that sentence only going from a vector that represents the other sentence.
That's interesting. So would this approach with the autoencoding be more inclined to produce exact duplicate outputs?
That is the goal. That is, the teacher is not telling it you're wrong necessarily, but how wrong you are in your own reconstruction. The teacher is not necessarily telling it a binary outcome, like you are wrong, 0 or 1, which is usually when you tell it cat or no cat. Either it is or not, but if you're telling it to reconstruct this input output,
you can be close. It could be you're
Right.
almost there, you're not almost there.
Exactly.
Completely different. Okay. Yeah, I think it's fascinating to have these conversations in the context of machine learning, and it obviously brings to mind how people learn. Is that something that you've encountered in your field about similarities and difference between human learning and machine learning?
Yes, machine learning was, well, this particular field of neural networks within machine learning, its whole goal was to try to replicate what's happening in the human brain. And this idea of neurons that have dendrites, synapses, and all these elements that connect to other neurons. And one neuron, depending on the stimulation, could fire up and give an electrical impulse that can stimulate other neurons and have a cascading effect. And that will make our brains do or react in certain ways. So that process has been trying to be replicated in neural networks specifically, but of course there are some limitations. We know that the brain has a tremendous amount of neurons, and the way they're connected, it almost looks random, but it's not random. And in machine learning and neural networks, we have to be very careful on how we structure these neurons. We should put layers, hidden layers, input-output layers, and things attached to these neurons so that they can become as good as neurons in the brain. These neurons are trained using backpropagation, this algorithm that is the teacher and the student. And our brains work a little bit differently. Our brains sometimes are very self-supervised, and sometimes when we're growing up, I think we just burn ourselves with something, or we cut ourselves, or we fall down, and that's how we learn, by pain or happiness or emotional responses to things. And that process is drastically different. There is no gradient descent happening inside of our brain, but that's why this algorithm, the backpropagation algorithm, was really good at making something learn in the way that we would like to have it in neural networks.
This has been very, very informative. I think it would be helpful to just touch on a few technical challenges in the field and talk about some limitations in what AI models and large language models can do, just to get a sense of how is this similar and different to what people might imagine in their head when they're thinking about what computers can do. Are there any specific challenges that you've encountered that you think are holding back AI models right now?
There are challenges today that I think have to do with compute power. Things have been great recently, thanks to GPUs, for example. We can do a lot of training at large scales, thanks to these learning algorithms that are scalable and allow us to execute training phases in multiple computers across many nodes in the cloud or in-house, whatever you like. And that has been great. However, I think that is not accessible right now to most academic institutions, and only certain companies and some government institutions may have access to this kind of power. I believe that is limiting what we can do with AI. So if we're thinking that industry by far controls what we can do with AI, you can imagine that's going to be driven by profit, growth, or positioning in the market. While academic institutions, we do things for different reasons, sometimes for the sake of science and curiosity. And so I think that is a problem, and that is not letting AI go to a better place right now. Now, the government is making a lot of efforts in making this more accessible to institutions, and they're making great advances. So I think that will change soon. Beyond compute power, I think what is also limiting AI is that we are still thinking on this side of narrow AI, that we can go a little bit higher without going to general AI or to wide AI. We should be able to move forward to more multiple modalities of AI. For example, they understand text and images, or video and sounds, x-rays, a wide variety of data at the same time. So I think it's coming in the future. Also AI that puts together things that are very simple individually, but solve a very complex task together. One author called Daniel Kahneman wrote a book called Thinking Fast and Slow. He was talking about two types of thinking: system one thinking, system two thinking. System one thinking, he explains it, I think, in a very good example, that if you are driving in a very familiar road and go to your house, for example, without knowing that you were driving, sometimes you get there and say, oh, I don't remember driving, because you're familiar with the road, you're familiar with the car, and conditions are perfect. So your brain is somewhere else solving other tasks because it was very good at that. But change that to when you're in a rented car in a city that you've never driven before, and there's people yelling in the back of the car, and you don't know where you're going and you're lost. There's a point when your brain says, stop talking to me. You turn on the volume as if silence is going to help you figure out what you are. It's when you need your full attention, all your senses, and your brain needs everything to be focused in one task. That is the type of system two thinking that I think is the next thing in the game of AI.
So right now you'd say AI is more system one.
Right. We're very good at system one, but I think system two is the next challenge that we need to solve, that we take all these pieces that we're very good at to solve a very challenging, complex task.
That's where we'll end today. Thank you for listening to AI Council Code. We're so glad that you joined us today. Stay tuned for additional podcasts and more insights on AI legal issues.
Thank you for listening to this BakerBots podcast. BakerBots has the experience, knowledge, and people to address our clients' most significant legal issues. For more information on BakerBots practices, please visit us at bakerbots.com. This presentation is provided by BakerBots LLP for educational and informational purposes only. It is not legal advice and is not intended to establish an attorney-client relationship. Under the rules of certain jurisdictions, this communication may constitute attorney advertising.